Okay, feast your eyes on this integral. We have x cosine x. And you'll notice pretty quickly that our usual substitution method is not going to work on this one. What we need is a different method, and that method is called integration by parts. Now, let me show you how it works. Let's suppose we have a couple of functions, u of x and v of x. Okay, u and v, of course, are functions of x, and I want to find the derivative of their product. And I'll just use differential notation here. So I'm going to use the product rule, of course. So now what I'm going to do is I'm going to take the derivative of the second times the first. So this is going to be u dv, right? Derivative of v times u plus v du, the second times the derivative of the first. So this is just the product rule. That's all this is. So I differentiate it. Now that I've done that using the product rule, let me go the other way and integrate both sides. So I'm going to integrate both sides. Okay, so I'm going to have the integral of u dv plus the integral of v du. So I just integrate it through. Now, of course, over here when we integrate this derivative, we get uv. And then all of these still have the integral with them. Yeah. Now I'm going to do just a little bit of rearranging here. I'm going to keep this one where it is, and I'm going to move this integral here over here with the uv. So what I'm going to have is this. I'll have the integral of u dv equals uv minus the integral of v du. This right here, this is the formula, if you will, for integration by parts. So let's see how it's going to work. We've got our integral x cosine x dx. Now, the way this works, integration by parts, I view this, all of this part right here, as being two parts, a u part and a dv part. So here's the way I approach it. I'm going to say, okay, let u be x in this case. And then immediately I say, well, then du is equal to dx. So that feels an awful lot like substitution. Now, I've let u be x. Now, dv is going to be the rest of it. Cosine x dx. That's the rest of it. So now, here's where it differs. Now I'm going to find the antiderivative, an antiderivative for cosine x. So that would be sine x. So now I find v is equal to sine x. Now I don't have to put plus c because I only want one antiderivative. So I've got dv equals cosine x dx. Well, what is v? Well, I integrate. I find the antiderivative. And the antiderivative of cosine is sine. And I don't need the constant. Now, let's use our formula. The formula says uv, so there's uv. So this is going to be x sine x minus, see, just going right along here, v sine x okay, see that? Du. Du is just dx. Now we can manage this integral. No worries. So we've got x sine x minus the antiderivative of sine is, well, I'll just keep this negative out here. It's negative cosine, right? And now I'll put the constant. Now let's see what we've got here. We've got x sine x plus cosine x plus c. And there is our antiderivative. So that's how we could approach this integral using integration by parts. Now, I want to point out something. There may have been a question, well, how do you know what u is and how do you know what dv is? How can you make a wise choice? Well, notice what what was vexing us with this problem here was that we had an x cosine x. The fact that that cosine here was with this x. Well, I know that and notice that when I assign u, I'm going to differentiate u. Well, what happens when we differentiate a polynomial? It decreases in power. So I had x to the first power. When I differentiated it, it went away, x to the 0 power. So that means when I end up over here with v du, well, I'm going to have a very simple integral. The x is gone. See? So that's what we were working toward, is we chose u with the idea that when we get this integral over here, we'll have a simpler integral. Here I had x cosine x, and here I just have sine x. And that's because we let u equal x. Now, if we had let dv equal x, then we would end up over here with a 1/2 x squared. And our situation would have been worsened, right? So instead of x being diminished, and we just have a simple integral over here, we would have a 1/2 x squared in addition to the trig function. So that was our motivation in letting u be x instead of dv being x. Okay, let's look at another one. Let's suppose I've got x squared e to the 3x. Now this is another integration by parts one, and you can recognize these a lot of times because notice we have this exponential function here and a polynomial here, and it's a product. A lot of times when you have a situation like that, it's calling for integration by parts. So we're going to use this right here. Now remember, it's time that I decide what I want to let u equal. And remember that the idea is I want an integral here at the end that I can evaluate. I want to be able to find the antiderivative for this. So I'm going to let u equal x squared because I know that when I find du, that's going to reduce this in power. So I've got 2x dx. Next, I let dv equal the rest of it, e to the 3x dx. And I find an antiderivative of that, which you got to be careful here because remember, you're getting the antiderivative. You're not differentiating. So it's going to be 1/3, well, v is equal to 1/3 e to the 3x. Remember, you divide by the derivative of the exponent. Okay? So a common mistake would be someone would multiply by 3. In other words, they would differentiate. So you got to be careful. Now, let's see what we have. We're going to have uv. Okay, so here's uv. So this is 1/3 x squared e to the 3x. Okay, so there's uv. And now minus v du. So the integral of v du. So let's see here. V is 1/3 e to the 3x. Okay, so there's v, and here's du, 2x dx. There. So uv minus the integral of v du. Now I'm going to rearrange this a little bit. Because it's kind of messy here. So here's what we've got. We've got 1/3 x squared e to the 3x minus, let me pull these constants out here, 2/3 integral x e to the 3x. Now we've just got to find this antiderivative. We've got to integrate this. But the problem is I've still got an x here. So we find ourselves in a better position than we were here because we had an x squared, but still, we have an integration by parts problem here. So I need to do integration by parts again. So I'm going to take this integral right here, and start from scratch. I'm going to integrate this as though it's a brand new problem. So I'm going to do this. For this one, I'm going to let u1, let me just call it u1 equal x. Then du1 equals dx. And dv is going to be just like before, e to the 3x dx. So that means that v is equal to 1/3 e to the 3x. Now, let's go back here and see what we have. So let me just write the whole thing over. We've got the original, x squared e to the 3x. And let's just see what we have here. We have 1/3. See, this is what we had before. 1/3 x squared e to the 3x, right there, minus 2/3. Now, in place of this integral, I'm going to put this. I'm going to put what we found with integration by parts. So we have uv, see, uv, so that's going to be x e to the 3x minus v, see, there's v, and I'm going to put this in there, du. See? So here is v, 1/3 e to the 3x, 1/3 e to the 3x, and du is just dx. Now we can deal with this integral. This is easy for us. So let's see what we have now. We have 1/3 x squared e to the 3x minus, let's see here, this is going to be 2/9 x e to the 3x. See, just distributing through. Minus, or look at this, minus times a minus, that's going to be a plus 2/9. 2/9 times the antiderivative of this, which is 1/3 e to the 3x plus c. And you can see we can go a little further with this. So this is 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus 2/27 e to the 3x plus c. And there we have it. So this was an example of we had to use integration by parts twice.